Okay, so good morning. We begin our lecture today and we continue our study of the ideal gas in the canonical answer. I keep using these words so that you get familiar with it. Okay, so when I say canonical ensemble, the picture you should have in mind is your system in contact with a heat bath at some temperature T. Okay, so that gives you one parameter, and that's about it. That's all we need to know about the system. And so last lecture we saw that uh, we could write the partition function of this thing as okay by dividing out by n factorial, so that only type 1 configurations this thing, contribute. Okay, so this is an approximate thing, and but we can do exact computations also, but this is approximate. And so we actually obtain. So we did one thing, right? What did we show? We showed. So we used this and we computed the internal energy U. I use the symbol U here because that's what is used in thermodynamics. But for us, it is just the expectation value of E, and this turned out to be 3n by 2 kb2. Okay. So, are there any questions with respect to what we discussed last lecture and these few points? Okay. If not, today we will compute the expression of pressure. Okay. So, so let's do that. So the first thing is, so let us kind of understand what pressure means. Okay, so microscopically, what is happening is that the particles of the gas bounce off. Right, so that's what is going on. The bounce of the balls, and so obviously, there is a momentum transfer in the process. Okay, so one way would be to go ahead and compute on an average how many particles will do hit the wall and work out what their velocity distribution is, etc. This looks pretty complicated, but we won't use this. But this is where the where pressure arises. So there's a momentum transfer. That means there's an impulse. What is impulse is force per unit time, but then you have to from that and there's some area you have to divide out. Then you have to work out some time in the problem, etc. So we can do that, but I'm not going to do that. Okay, so what we're going to do is what we will see is that so we pick a particle. Okay, and we will assume that the setting is a cubical box, sides L1, L2, L3. Okay, even though we will do computations for a cubical box, we will later write the answer. We pick a particle and ask how its energy changes as the length scale, as L1 is changed. Okay, so I'll write. Let's be more specific. Let epsilon r be a particular microstate. Okay, and if you remember from the quantum thing that there was some dependence on this thing, so the force the particle would exert. So we can define this, and I ask you to think about the sign. I won't explain the sign today. This. So as we change L1, okay, so at least dimensionally you can check force into length is the work, right? So work done by the system, this thing, etc. So you can see what expansion would do, and so from that you can work this out. Okay, so this would be kind of a microscopic formula, but we know that so we want to work out what is the average force. How should I do this? Due to this particle. Anybody? I haven't finished writing my sentence, but what should you do? So we know what is the force if it were in a particular state. How would we carry out the ensemble average? We should carry out an ensemble average, right? It won't be in this state because it can be in any of the states. So what should we write?
So integral over all states into density of states into e to the power minus.
Okay, I'll just write a simpler. I'll write it in a slightly different form. Sum over all states R, okay, times minus d epsilon r by dl1 e power minus beta. Okay, is this fine? And I should divide. This is not correct because I have to divide by the probability. This is what we should do, right? Because 1 by z e power minus beta er is the probability of finding the system in state r. Is this formula clear? Okay, so we can simplify this a little bit more. We can rewrite this as follows. We can write it as 1 by z d by dl1 of okay. But when I differentiate this with respect, pick the term, we have to divide out by a beta. There will be a beta which will come down, beta epsilon, right? You take this derivative through the things, through the summation, and okay. So it's easy to see that this formula goes to be about that. Okay, but what is this? What is this quantity?
The partition
Shell.
function.
Yeah, 1 by, yeah. So actually, one mistake I made here is just we are doing it for one particle, so I should write little z, okay? Right? So this is equal to 1 by little z beta d by dl1 of z, which we can write again as kbt. Beta is 1 by kbt, so beta d by dl1 of log z. Okay, so now we have got something. This is our formula. If we want pressure, so this is acting on the wall, one of the walls, okay, along the x-axis. So what is the area of that thing? So it can hit anywhere in that box. So the pressure, okay, so the pressure, contribution to pressure from this one particle is, what should I do? I should divide by the area. But what is that area? What is the area of that side, that face? It's a cubical box.
It's L square.
It's actually L2, L3,
Yeah.
okay? Because we didn't, I didn't take cubical, actually cuboidal. I wrote cubical, but I actually wrote cuboidal. Let's correct that. Right? Sorry. Yeah, L square. Actually, it doesn't matter because the final answer we'll write in a nice way. Okay? But what I will do is, we know that L1, L2, L3 is the volume, and we want to write it in a, we want to write a formula which is valid not just for cubical box, for any box. And that's the way to go. So this would just tell you for a cubical box. So we get a formula which is true not just for a cubical box, but much more general. But, okay, so this is due to one particle. So pressure will be n times, so there are n particles, so each of them will act, n times F divided by L1, L2, and this is equal to kBt, n kBt, d log z by dV.
So shouldn't it be L2, L3 in the denominator of average F?
Absolutely. I wrote it correct in one spot, but not in the other ones. Yeah. Thanks. Very good. Anything else? Okay. So now I can go back and take this in here and write this as kBt times log. Okay. And with no loss of generality, I can replace z power n by z power n by n factorial. Right? Why is that? Because it's inside the derivative with respect to v, and that n factorial will just get cancelled by that. So this is equal to kBt times d log z by. Okay, so we get a formula which says that pressure equal to kBt. Okay, so this is really a statement which you have got, and this is valid. This is a general statement. Okay, and this is a formula worth remembering. Okay, so I'll pause here for questions.
Sir, can you repeat how you went from small z to capital Z?
Yeah. So first thing I did, so this is the formula we got. Okay, but I can take n log z is just log z power n, little z power n.
Yeah.
Okay, so what I'm saying is that I'm using the fact that d by dv of log of n factorial is 0, because v is independent of n.
Okay, sir.
Okay, so I can divide by n factorial. So from here to here, I use that step. Okay.
Sir, how did L1, L2, del L3, that part become del V?
That's just partial. I mean, we are only varying L1, right? We're asking how L1 changing. So the change in volume. Yeah, good question. So what I want to say is that dV. So in this thing, when you're looking at a particular void, we are keeping L2, L3 fixed. We are not changing it. We are asking, okay, but I'm changing L1. Okay, so what I'm saying here is delta V in that instance is L2, L3.
Got it, sir.
Good. Keep asking. I mean, there's no, I mean, these are, I mean, for me, it's obvious, but I didn't state this, right? Okay, so because you're asking for the force along on that L2, L3 plane, right? So the plane of
Yes,
size
sir.
L2, L3. So we just want to know how much, if we move that, how much it changes, right? So that's really the core of this statement here. Okay. But what is very pleasing is that that this is a formula which we are able to derive from first principles. Okay, so now you can see here. So how are we going to do averages? We do the ensemble average and ask what it gives. Okay, and we get a formula. But what is very cool about this formula is that it really is not specific to the ideal gas in per se. We didn't have. Yeah, okay, so it can be true for quantum gases, other systems, etc., etc. And so one more thing, recall I said that there is a state function. Again, I have explained, but there we'll have a lecture. The state function in thermodynamics. Okay, called the Helmholtz free energy. Which I said, which I used the symbol F, okay, and said that F was a function of T, N, and V in our example, and this was defined to be what? Minus KBT log Z. Okay, again, this is a very universal. So right hand side is the StatMech object, left hand side is the thermodynamics object. Okay, what is the state function? So in thermodynamics, you're a macroscopic system and you're specifying the state macroscopically by, in this case, by specifying the temperature, the number of particles, and the volume. These are the control parameters of the state variables which specify the macroscopic state. And then depending on so this depends on an experiment, etc. So you could have entropy as your state function. And so if you have these three fixed, you work with the Helmholtz free energy. You must have heard things like enthalpy, etc. We'll see in what context. So it really it depends on what is the macroscopic experiment doing. Are we doing a constant volume experiment? Are we doing a constant temperature experiment? Are we doing an experiment keeping pressure constant but letting volume vary? So depending on that, in thermodynamics, you will introduce state functions which describe various things. So if you make this correspondence, then we get a formula which we can compare with. So let's go back here. So KBT log Z, again KBT is independent, so I can take it inside the derivative. So we get this formula for pressure which says it is minus dF by dV. Okay. This is a standard formula. In thermodynamics. Okay, but what I am trying to say here is that this formula is very important. So this is the backbone of the connection we can make from the canonical ensemble to thermodynamics. So if our system is isolated, we don't work. What will be our state function if our state, which we should match in thermodynamics? So isolated system will specify the internal energy, not temperature. number might be constant, volume is fixed. So what will be that object? Somebody?
So can you repeat?
Yeah. So what do you think will be the thermodynamic state function that you would use for an isolated system where energy is conserved, total energy is fixed, number is fixed, and of course volume. What would be the state? I didn't use the word state function, but we wrote some funda formula, right? The analog of this.
Entropy.
Exactly. It will be entropy. That's it. So we already seen two examples of state functions, and okay. So now we are ready. So we have a formula. And let us compute the pressure. So, so we'll go back to our, so what was the pressure? It was kVt times log d by d, right? This was it. And but if you remember, we had done this computation for Z, and if you remember, Z was what was Z? But we really need only okay. There was some 2 pi m kBt power 3 half or something like that, right? But all those terms do not depend on V, and we know we're going to take a derivative. So this is all I need, right? Do you agree? To compute pressure, I know other terms will not contribute because the formula for pressure involves only a partial derivative with respect to V. That means keep other things constant, keep n constant, keep what is the other thing? T constant. Is that okay? So what do you agree?
Yes, sir.
Okay, good. So now we can just take this thing. So we get P equal to kBt, and derivative of log V is 1 by V, so it becomes n by V. Okay, so we get PV equal to n kB times T. This is something which we are taught in high school. This is the ideal gas law. Except nobody told you what was ideal about this. Okay, at least here we said we have particles which are independent, they're non-interacting. So we have something much more well defined. Okay, but is this the way you saw ideal gas law in high school?
NRT.
NRT, right? So in high school, we wrote and what was N here?
Number of moles.
And how many particles does 1 mole of a gas have?
Avogadro number.
It's approximately some 16 to 10 power 23, right? Particles. Okay, so what we get is N is nothing but little n times Na, or little n. Okay, so just looking at that, we can compare these two guys and we get a relationship between. So R is Avogadro's number. Okay, so in physics, in our course, we'll never work with R, but we'll work with Boltzmann's constant Kb. But actually, you see, that's a very, very simple relationship between R and Kb. Okay, is this clear? Okay. So did you guys already know this? I mean, before in BSc you must have learned this, right?
Yes, sir.
Okay, good. Sorry, I didn't go through a BSc program, so I don't know what's taught in BSc. So okay. So this is so we actually recover the ideal gas law, and then we can. So we have now. So we have done two computations. We found that the internal energy was equal to 2 by 3 by 2 nkBT, and pressure equal to. Okay. So what we get is we get just one more statement here. Coming back to this is that you can see that pressure is a intensive variable. So if you can see if you scale, so what is an intensive variable? There are in the thermodynamic variables, state variables, there can be intensive objects and extensive objects. So temperature is supposed to be intensive. N depends on the size of the system. You double N and double volume, everything will remain the same. So V is extensive and P is. So N by V, which is the number density, is an intensive variable. Okay, so again, so we should just remember P is an intensive variable. This is something which, and it is pleasing to see that we get P equal to N by V, which is an intensive number. If you divide any two intensive variables, you get an extensive variables, you get an intensive variable. Okay, is this clear? The notion of an intensive variable. So pressure is intensive variable. Okay, so what we get is let's define energy density to be U by V. Okay, so then we can just go ahead and divide these two things. So what we get is P by U equal to, put not capital U, little u. What is it equal to? 2 by 3. Pretty cool formula. Okay, so turns out, and we will see that this formula holds for your quantum gases. Okay, even though the ideal gas law doesn't hold. Okay, so what happens is that Pb by nkBT in those cases will be equal to 1 plus corrections. And similarly, U by nkBT will be 3 by 2 into 1 plus corrections. Okay, and so the point here, so the thing is that what is happening is, what I'm claiming here is that the corrections that appear in the ideal gas, so these are corrections to the ideal gas law, and this is corrections to the 3 by 2 nkBT kind of stuff, and these two corrections are the same. That's what one is saying. Okay, and there is a simple way to understand it. But I just don't want, I will not discuss it at this point in time, but we will see this thing. But rather, I'll give you an example where it is not. So, however, this is not true for a gas of photons, for instance. Okay, why? I mean, the reason is that these are relativistic. Okay, and the energy is proportional to c times the magnitude of the momentum. So this is the dispersion relation, which is not p square upon 2m, which is the case in all the other cases. Okay. So here, you must know about Stefan Boltzmann's law, right? So, which says that the energy density U is, let's write little u so that I don't, U by V is proportional to what power of T?
4.
Fourth power. Okay. So this is, and the constant is called the Stefan constant or something like that, right? Okay. So again, we will prove this. Okay. But you can see that, key thing in this case we will see is that the dispersion relation is the same. That's the energy momentum relation is the same for in the reason these corrections are the same is because of that. Okay, so we will see how these corrections come, etc., etc. And right now we will not discuss that. Okay, so I'll pause here for some questions and comments.
Sir, I just wanted to know that if you want to study the same system for relativistic gas, like not just for photons, but for like relativistic any kind of molecules or so, do we just need to consider the energy equals to root over p square s square plus m square c power 4? I mean, that change in the energy.
So yeah, for a massive relativistic particle, yes, that's what we have to do. Okay. Yeah, the Hamiltonian. Yeah, good question. So the question asked is for a relativistic massive, that means non-zero particle. We saw from last semester, or if you don't from somewhere else, or you just take whatever I'm saying was square root of p square c square plus m. This is what we should work. Okay, or write it as Hamiltonian. Okay. Yeah, absolutely. So we can work with this. But the point is, here is the important point to realize is that the formula that we are writing, so we have to compute the free energy, and if you want the pressure in that case, you can go ahead. You do this, you take F, you do dF by dV, and lo and behold, you'll get the pressure for that, for relativistic. You get substance. Okay. But definitely you'll see that, U won't be 3 by 2 kBT in that case, etc. Those things happen.
Okay, sir, got it.
Okay. Good question. Okay, so this is what I mean. The thing is that the reason why are we using the ideal gas? But let me get to. I'll discuss that after. I just want to discuss few properties of pressure. Only a couple, but so that's one thing which goes by the name of Pascal's law. So, how would you measure pressure inside a gas? You would put some small surface anywhere in the interior of the gas, and then you will measure the force on that surface if you know that area. Okay, so what it says is that the pressure is constant in all directions. Okay, So it's called, this is written as isotropy. There's no preferred term. Isotropy of pressure. Okay. The second way of saying the same thing is the pressure is a scalar. And so there is a definition which makes this clear, is that pressure is written as a trace of something called the stress tensor, which is a second rank tensor. Don't get scared, no? Just something which has, it's a symmetric, so this is just called the stress tensor. Okay, and this is something which you can compute in a fluid, things like that. And so this is one definition. And so the trace of any symmetric tensor is a scalar, we know. I mean, okay, this is a second rank tensor, so it transforms some particular way, but it's easy to prove that trace of a second rank tensor is a scalar. So these are the definitions of, these are some properties of the scalars that I wanted to mention. Okay, so
Sir, if we ignore gravity, then the pressure will also be homogeneous, right?
yeah. So in your next problem set, we will see, for instance, we will see how to work out the variation in pressure due to gravity. Okay, that's a problem in the problem set which will be coming later today. Okay, yeah, you're right. It will be even homogeneous. Oh, beautiful! I shut down my. Okay. So I want to just discuss the validity of our computation. Okay. So to do this, what we will do is we will look at a couple of numbers. Okay. So first thing is we will do is we will what we want to ask is what is the average spacing of particles. Okay, from dimensional grounds, it should be V by N power 1/3. This is one natural length scale in the problem. You agree? Is this, so this is one length scale. The second thing is the thermal wavelength. Which I will use H by P. This is the de Broglie relation. So they were just working out some, the idea here is I want to get some dimensionless number and then, okay. And so H by P, but what is P? P square is, M kBT. There are factors, but we don't want. And so let's move that and put square root. P is of the order of this. So we get a thermal length scale, which is H by M kBT power half. Okay. So what we can do is we can work out a ratio. So let's do thermal wavelength over average spacing. Okay. So that will be H by M kBT power 3/2 divided by this guy. So N by V power 1/3. Okay. So let us just, since there are cube roots, etc., and let's also, let me introduce some notation. Let N be number density, so N by V. So we get a nice dimensionless quantity. So let's call that lambda. I am cubing things, so that will be the cube of this quantity. So it will be n h cubed by m kBt. Nobody even complained I put a cubed here, half, right? Okay. So now, so the point here is, when is classical mechanics or the semi-classical computation valid? There are many ways of understanding this. So quantum H is a measure of, so I'll do it two ways. Okay. So first one is by just saying this thumb rule that quantum corrections, if I'm looking at quantum corrections, I require H to be 0. H sort of determines. So H being very, very small means quantum corrections would be. So lambda being much less than 1, okay, implies quantum corrections are suppressed. Okay, but but H going to 0 is not the only way. H is also not a free parameter that we have in real life, but we can. So the way to understand that is, so number density, so it should be n should be small. So densities or T should be large. These are also ways. High temperatures. So these were all statements I made earlier, and you can see that all these situations. Okay, so that means a gas is not very, very dense. Okay, so then, but at the end of the day, this lambda, which is a dimensionless object, is what controls things. And so, for instance, we wrote plus corrections, and those corrections, if they are quantum corrections, will be a function of lambda. Okay, so we saw something. So let's write this: PV by nkBt was equal to 1 plus order lambda. This is another way of writing it. So these okay, and so for instance, the coefficients in the lambda expansion are called virial coefficients. Okay, and one can compute them, and we'll compute at least one. At least we will correct for the quantum gases. We will compute these things. Okay, so let's come back to this and ask what coming back to the physical definition of lambda or lambda cubed. Thermal wavelength over average spacing. So lambda being small, that means the thermal wavelength is very, very small compared to the average spacing. That's what it means. So this is really how we can understand quantum correction. So thermal wavelength is, of course, determined by the quantum corrections, because we are using h by p out here in this formula. So it's a quantum. The only way you can have h coming into any story if there is a quantum aspect to it. Okay, so I think I'm done with what I wanted to say today. So I'll pause for questions. Yeah.
Add a comment to Mike on this physical interpretation of that ratio that you took.
Yeah.
I mean, like when we have thermal wavelength comparable to the average spacing, then the particle waves can, of two particles can interact with each other, and then we can't take them as individual particles.
Yeah, this is a beautiful picture. Yes. Absolutely.
Yes, and then we need to take the quantum effects into consideration.
Absolutely. Okay. So for instance, this is absolutely right. So what you should, so the picture, so I'll draw a picture here which will explain that same statement. So what you should think of, what we think of as point particles, really in quantum mechanics, they are not that, but they are actually objects which have some size. And this size is the de Broglie wavelength. Right? So which is of course determined by its momentum. So there is a fuzziness, and this is estimate. This is similar to how we said a point in phase space will become fuzzy. Similar to that. I mean, it's similar in spirit, but this is just something like that. So this is if you have a situation like this, then what you would say is that quantum corrections can be neglected. But now if you have a situation where we have something like this, and okay, here we cannot neglect. Okay, but that's a very interesting question, because we can ask is that, you see, all particles don't have the same de Broglie wavelength, right? So, but so there can be particles which have very, very, very high energy, or so rather whose de Broglie wavelength is fairly large, but that won't be typical. The probability of such events are fairly small. Similarly, when we are integrating over all momenta, okay, so we are going up to infinity, and obviously there are it becomes relativistic. So again, we can ask what about relativistic effects? Okay, then you have to compare. What you have to do is that you have to compare the momentum with the what is called m times c. This has a name, I forget. Doesn't matter. As long as so you will find that the typical values of p, as long as they are less than m times c, you don't have to worry about relativistic corrections. So this is the power of dimension analysis. Special relativity brings a parameter called c. Quantum mechanics brings a parameter called h. And so as long as you're able to control, so you can construct dimensionless quantities, which will tell you when to worry about such corrections. So this method which I've used is fairly general. Okay, so, and thanks for suggesting this picture. This is a beautiful picture, and this is roughly what one is saying. Okay, so let me stop recording.